Today. The topic is transformer networks, which is well the topic of the moment, and will be today is in this lecture we are going to see attention is all you need, the definition of transformer architecture. Then we're going to discuss transfer learning, particularly pre-training, zero-shot and few-shot learning as it pertains to the architectural issues on transformers, and we're close discussing the architecture of popular models like BERT, GPT, T5, and other variants. So it's a key lecture, particularly this. We're going to refer to it a lot 2 lectures from now when we see multimedia processing architectures. If you have some interest in reading the papers that are on the paper pile for the seminar, I highly recommend, if you only have time to read one paper, read this one, the Tianyang, Lin, and co-authors, many co-authors, paper from last year, A Survey of Transformers. That paper will give you a very good understanding of all the different variants of transformers, of all the work that has been done recently on the field. I mean, the amount of research sparked by transformers is truly unprecedented. And interestingly, even though there is so much work, there is still plenty of space for innovate. Something that is quite curious about the transformers is that they have a massive amount of parameters, but once they are finished training, their attention tables contain a lot of zeros. Yes, that fact is used by distillation systems that we will see on the last lecture on network architecture search. Yeah, but that means that they are quite inefficient in terms of the way they use the data and the computational resources. So, well, this is beautiful. We have a system that works, it has a lot of research on it, and there is still a place to innovate. But before we look at them in detail, I want to revisit from last lecture the concept of alignment. Particularly, I want to tie it back to where the whole concept originates, which is in natural language processing, more particularly in machine translation. Yes, so in machine translation, by statistical means, we have alignment tables, yes, where you can say the word Zone économique européenne, yes, aligns to European Economic Area. Yeah, and they are, in general, most text in machine translation is aligned following the diagonal. But those words, the Zone économique européenne, it's the opposite order in French from English, yes? So then you have this counter line there in the center. So people in statistical machine translation were working on building this alignment table for a long while, and it was something that they had in mind. And in a way, this type of alignment tables, the intention of bringing attention mechanisms was to use this type of technology for recurrent neural networks, encoder-decoders. Yeah, and that's the paper from Badano and co-author from 2015, and they define an attention mechanism that is quite different from the attention mechanism that is used in transformers, and we are going to discuss today, and let's call it Badano attention. Yes, but as we saw last lecture, the whole idea of the attention mechanism is to produce a statistical summary of the intermediate outputs of the encoder that are then fed when we are decoding a particular element. And in the case of Badano attention, that is achieved by using a full neural network, yes, that is trained to produce this statistical summary. But this is, of course, very expensive because we have to execute this neural net for each of the elements. Also, last class, we saw the neural Turing machines that arrived to this idea of attention more as a retrieval mechanism. And the retrieval mechanism is the technique that is used in transformers. The reason I bring this simple attention is because, at least when I was studying this topic, I found simple attention easier to understand conceptually, and then move into the full attention system as used in transformers is a simpler transition. Yeah. But overall, the idea is that we want to have a way of summarizing a larger context as it pertains to a particular situation or model. Yeah, and we can do it by position, we can do it by word. Yes, the important aspect of this attention is that it brings the world to one particular point. And as we saw last class, then with this attention mechanism defined in RNN encoder-decoder systems, systems become able to handle much longer inputs and outputs. Yes, however, they still have a big training bottleneck. Why? Because to train them, you need to assemble mini batches. Yeah, and these mini batches have to have sequences of the same length. So you can, well, as you are unrolling the recurrent neural net, then the neural net becomes only one network of that particular number of layers. So if you have a sequence of length 10, it's a network with 10 layers, and if you have a sequence of length 20, it's a network with 20 layers. Yeah, and while all the layers have the same weights, if you want to train them in a mini batch, you have to have them in the same mini batch, which in turn means that very long sequences, which are rare events, have very poor gradients because their mini batches are very empty. Yeah, and also, well, of course, training this is a big headache. So that's one of the problems. Because we're receiving and then when we're training, we're receiving the input one at a time. That's also a big problem. Compare that to CNNs that can see the little window over which the CNN operates all at once. Yeah. So Vaswani and co-authors, what they realize in Attention Is All You Need is that you don't need the recurrent neural networks. Yes, that you can operate using attention mechanisms all at once directly from the sequence. Yes, but if you receive the sequence all at once, the neurons have no underlying ordering about them. So in the input, there is no way to know which element is the first or the second. They are all like floating there. Yes, and then they use positional embeddings to capture this positional information. Then in Attention Is All You Need, what you get is this encoder-decoder system that is exclusively based in attentions. You have an input to take these positional embeddings. Then you have multi-head attentions with residual links and layer normalization, feed-forward neural network of size 1, plus another additional normalization. In the encoding system, we have self-attention plus cross-attention during the decoding. And also the decoding incorporates mask inputs, yes? And these are all buzzwords or concepts that are key to understanding all Attention Is All You Need and transformers. And different from the previous lectures, in this case, we're going to go through them one by one in detail, given the importance of transformers. So, but the no attention, as using a trained neural network, yes, needs to be executed as many times as you have items in the memory. Yes, because you have to produce the score for each of these elements in the context to produce the summary. Instead, that's why people in general do not use button attention, because it's slow and expensive. Instead, they use a technique in transformers that is derived from the neural Turing machine, where you have the concept of keys and values and queries, yes? So what you are trying is to project everything to a common space and then use a similarity metric, that is the dot product, to obtain the weighting for each of these intermediate, these values you are trying to fetch, yeah? But then, of course, the question is, what is the query and what is the key? In formulas, the attention, yes, is just a softmax of taking the dot product between the queries and the keys, yeah? So that's the attention mechanism, and you multiply that for the values and you get the output of the attention mechanism. In self-attention, yes, so the attention we saw last lecture was cross-attention, is to get the intermediate outputs of the encoder summarized to be used during the coding, yes? So there we say that the decoder attends to the output of the encoder, yeah? But in transformers, the encoder, yes, is also using attention, yes? So, but cannot do cross-attention because it's just starting the whole process. So in that situation, the encoder attends to itself. That's what is called self-attention, where the queries and the keys and the values all come from the previous layer of the decoder. Yeah? But the great property of the transformers is that the output for a given token then can incorporate information from any other token. Yes? And in the case of the decoder, we have cross-attention, as before, where the queries come from the previous decoder layer, and the keys and the values come from the output of the encoder. All right. So the other concept that is key to understand transformers is the idea of masked self-attention. Yes. One of the problems with receiving all the input at once is when you are training, you also have all the output at once. But when you are executing the system, you actually don't have the output, right? That's why you are executing a model, is because you don't have an output. So when you execute the system, you're going to be getting one token at a time, yeah? And in that case, then a mask is applied to these future values, so the system cannot use them to do decoding, because well, you won't have those future values at execution time. Okay, so with this we have a conceptual system, let's go back to it, that takes these inputs, does this combination of the embeddings for each of the different tokens, producing new tokens, yes? So this is transforming something from, say, one alphabet to another, yes? It's each of these blocks is producing an output that is similar to the input, but is conceptually it's like in another language, let's say, and but each attention mechanism in general doesn't have a lot of expressivity, yeah? So to be able to capture different aspects of the input, then we just stack them. So that's what is called multi-head attention, yes? So we just repeat the whole attention, yes? Because one attention alone just can capture certain idiosyncrasies in the input, but not all the power, all the complexities, yes? So we just repeat all these attentions, all these tables that need to be trained, with different components that are called heads, yes, and they are initialized with different random numbers, so we can expect them, we hope that they will attend to different issues, yes, so we hope that they will capture different idiosyncrasies in the input, but they might not, yes, and there is research in adding to the loss function regularization components so that to make sure that the multi-heads are actually different from each other. So, as such, then we have the queries, the keys, they do a matrix multiplication, we scale them, we mask them in case of the output, we apply softmax, that with a matrix multiplication give us the values, and this will give us the output of the attention mechanism, and we repeat this multiple times, and we get a multi-head attention. This should be one of the key things about this is that while this is all trainable by support stochastic gradient descent, this is quite different from the neural networks we're used to. Yes, this is a very different architecture. And after we have that, then we have a pointwise feed-forward network, which we saw in when we look at CNNs. They are quite popular in computer vision as a way of doing feature expansion or feature reduction. Here is just a trainable normalization step because this is they have the same number of inputs and outputs. Yeah. And they are referred as pointwise feed-forward networks. Another thing that the transformer block incorporates is a layer normalization. Yes, that we treat all features as the same and normalize, moving them to Gaussian units. And this is intended to avoid the numbers to explode, basically. And one of the problems of stacking transformer networks to make deep transformer networks is that they suffer from what's called token smashing, where the signal is lost and the outputs start looking the same for all inputs. Yeah, and this is similar to the problem we saw on CNNs, where adding more layers decrease performance. So to avoid that, you have the same trick that was used in CNNs. You have a residual connection from the previous transformer, so then the transformer cell start learning the errors rather than creating a new output. Yes, so this dampens the effect of the attention, but avoids token smashing. And to conclude, the positional embeddings, yes, because the network sees this whole sequence all at once, and there is no concept of first element versus second versus last. Yeah, we need to provide them some way to differentiate these elements by their position. Yeah, and interestingly, some applications we will see later on in multimedia do take advantage of the fact that the networks see the application all at once, and the elements don't necessarily have a very specific ordering. Yeah, but for a linear sequence to be a transducer, a sequence-to-sequence system, yeah, what we add is a positional embedding. It can be learned, but in general, just using a cosine of an angle derived from the position is enough. And the positional embeddings can be visualized in this manner. Yeah, and what this means is that each input is a word token. Yes. So then, for different positions in the embedding, in the word token embedding, we add the sine and the cosine of certain angles that are derived from the actual position, and for different coordinates we use the sine, and for others we use the cosine. And one of the interesting things that this approach that is described in detail in the paper, has a rationale that is they use wavelengths from a geometric progression from 2p to 10,000 times 2p because they believe that this way the system can learn to attend to relative positions. Yes, because using this type of wavelengths, then you can represent a position plus k as a linear function of the original position. Okay, so continuing. A transformer network is then a special type of neural network that repeats the transformer cell. We can think of it, the transformer cell, then as an everything against everything combination followed by a CNN1 for feature generation. In the encoder-decoder setting, the encoder uses self-attention, while the decoder uses cross-attention, and the decoder is trained via mask learning. That's the definition of what a transformer is. What we get then is a different way of seeing. Then this is what we saw in the first section. We get the inputs with these embeddings. We add the positional embeddings. We have multi-head attention with residual layers plus normalization. Then the point-wise feed-forward network, like a CNN of size 1. And this does the encoding does self-attention, and the decoding does cross-attention. And we also have this self-mask that is highlighted there on the side, used for training. And that is what is about to transformers. Now they have an incredible expressive power, but it's not without problems. Yes, they lack inductive bias, which leads to overfitting unless the amount of training data is an order of magnitude or more larger than the one you will need for an RNN. They suffer from token smashing, so extra mechanisms are added to avoid losing signal after many layers, and the attention tables end up being sparse in practice, which means that they should be possible to train them with less parameters. So, if they lack an inductive bias, means that a transformer network needs to train over so many data, how useful are they? Well, in practice, it turns out that they're very useful, because once they are trained, they allow for task-dependent fine-tuning. The initial task, is a task where they have been pre-trained, like next sentence prediction in BERT, and it needs computer power. So the beauty of task-dependent fine-tuning is that it needs much less computing power to do that fine-tuning than the initial training. So that makes it possible to people without GPUs. And this is a particular case of transfer learning. Yes, transfer learning is the idea of using knowledge gained solved in a particular task to solve a second task. And the interesting thing is that the initial task doesn't need to be a task that is on itself useful. Yes, and that's what we call pre-training. This task is a supervised task in general, but it's a supervised task where we know that where the labels are trivially available. And we can think of pre-training as learning the domain, basically like learning natural language processing. The auxiliary task is taken such that it's supervised, and then the labels are trivially available. An example of that includes, for example, masking a word and try to recover it, or concatenate two sentences and decide whether they appear continuously in some text or not. In the case of transformers, the transfer learning is achieved by fine-tuning. Yes, it can involve adding more layers to the network, so add an extra layer at the end and just train that layer. It could involve using multiple versions of the whole network in an end-to-end ensemble task. It normally involves using training data for the new task, but this training data is 2 to 3 orders of magnitude smaller than the original data used for pre-training, and then this whole system is then trained end-to-end. For me, yes, given the small amount of training data that is used for fine-tuning and the insane number of parameters that these large models have, it feels like you are using data to tickle the parameter space. Yeah. Of course, if you were to run this data for a very long time, for many epochs, yes, you will destroy the value that is already there and overfit the larger system. So it has to have care not to overtrain with the new data, but on the other hand, you expect that this whole mammoth is changing. So, from the perspective of computer architecture, of neural network architecture, the beauty of the transfer learning is that you don't need to transfer just fine-tune the weights that you have there, but you can use this large network as a building block into a more complex solution. This is similar to what we saw with AlexNet and LeNets and other CNN systems for computer vision. Yes, we can take these pre-trained models as the backbone over which we build more complex solutions. In the particular case of GPT that we are going to see at the end of the lecture, in the original paper, they show a number of variants they can use. Yes, here the green box is a transformer that is already pre-trained, and they show in the paper how by modifying the type of inputs the system takes and adding a linear layer afterwards, they are able to use this same pre-trained transformer to do classification, entailment, similarity, and multiple choice. In the case of classification, they use a special token to start, then put the text they want to classify it, and then another special token to mean that is the end of the text, run it through the transformer, run it through this linear classifier, linear layer, and feed it to a softmax, and that is trained then end-to-end on a small number of systems, and that gives us the output. In the same way, you have entailment. You can have a special token that delimits the premise from the hypothesis. Entailment is the task of saying whether this particular hypothesis is supported by the premise. And here you feed it into the GPT system and into the a classifier. More interestingly for us from the neural network architecture is to repeat the transformer system twice, and then we can do similarity where we have two texts and we want to see how similar they are. And for this, what the system is building is a Siamese neural network, because both transformers will be fine-tuned with shared weights. And finally, we can even do multiple choice by running each of the different answers to transformers, run them through a linear system, and then do a softmax to try to find the right answers. So that's for fine-tuning and transfer learning. But what if we don't need absolutely any extra data? Yes, that is why if an ingenious engineer realizes that with the existing model as it is trained, it is possible to solve other problems without adding any extra data. Yeah, that's not learning at all. It's just figuring out how to make use of an existing system. And in this case, this is called a zero-shot learning, yes, because it uses no new data, shots, yes, to solve the task. An example would be to use a particular BERT output as a proxy for semantic coherence, yes. In practice, zero-shot learning is never. It still have some parameters that need to be tuned, and they like regularization, and they can be tuned by hand or with few data. What is called few-shot learning that we'll discuss next. And so similar to zero-shot, have a very small amount of training data, 1 or 2 examples per class. And what can we do with so little data? Yeah. In the case of cosine distance in the embedding space, the extra data can be used to learn a deformation of the space that is more suitable for the secondary task. So what dimensions are meaning carrying for the task? Of course, wouldn't do fine-tuning will be with more data will be better. Conceptually, yes, fine-tuning will be better, but that takes a lot of computer power and actually might not work. The fine-tuning might destroy the structure of the network to the point that is less useful. So instead, taking the output and applying, for example, these deformations may leave you better off. And also, if you have a system that can achieve great things doing few-shot learning, that also showcases the value of the model. Yes, and then there is a lot of interest in it to show the value of the model as such. Okay, so far we have seen attention is all you need. We have seen the transformer network architecture, the transformer cells, the different parts of it. Let's take a look now at the popular models that are in heavy use. I would like to start with BERT, even though GPT was proposed earlier. BERT these days is practically a synonym of natural language processing. It's incredible the impact and how spread the brand is. Yes, and the intention in BERT is you take the attention is all you need architecture, you train it to do a certain 2 auxiliary tasks that we're going to see next, and then you throw the decoder and you ship the encoder. So this system takes text, 4,000 subwords as input, and produce embeddings. And this is what BERT is about. And these embeddings are for the whole text, different from word embeddings. These are full text embeddings. So from this encoder trained this way, then you can do fine-tuning and do transfer learning for a wide variety of tasks. And the other interesting thing is, well, it uses attention over all tokens, and then it's trained. It takes advantage of the fact that over these sequences it can be trained in parallel using the mask attention we saw in the previous when we were discussing transformers. So in the paper for BERT, they compare themselves to GPT, which was already proposed, where GPT is just a decoder. Yes, and because it's a decoder, then the attention is always to the past. Yes, while in BERT is using attention over all tokens. And to an earlier model that was used also for transfer learning, that was based in LSTMs, in RNNs, called it ELMO. ELMO is no longer very popular. So the the task that BERT uses, yes, is that of taking a sentence. So it's basically an autoencoder. Yes, you take one sentence, one span of text, and then you try to reconstruct it. Yes, going through all the transformer network. But instead of trying to reconstruct the whole sentence, what you are trying is to find some words there that you have chosen at random to mask. Yes, so you have the whole sentence and these few words that are missing, and you try to rebuild it. So that's what BERT is about. That's one of the auxiliary tasks that BERT is trained. The second one is next sentence prediction. You take two sentences, you put a special token in between to indicate that there are two sentences, one starts and the other ends, and you try to predict whether they were contiguous in the text or not. Yeah, you can see that both of these tasks can be done. If you have text, you can produce training data for this. It's supervised training data, but it's you have plenty of data just from having naturally occurring text. I do find the text coherence, this sentence juxtaposition task very, very exciting and very useful on itself. Sadly, later experiments found that it wasn't useful, like it was hurting fine-tuning and transfer learning, and that's why there are variations of BERT, Roberta, for example, that don't use it. So this is what I have for BERT. Of course, please read the BERT paper if you are using it, and there is a very, very large number of systems that build on top of BERT, that modify BERT or use BERT as a subpart of a larger system, and they call themselves BERT2, which I do find that confusing for newcomers. Yes, if like a system that has name entity recognition using BERT, yes, is not really BERT. It's a system that has name entity recognition. BERT itself just takes text and produces embeddings. Okay, so now that we have an idea about how BERT works and what it is, we can go a little bit back in time and look at GPT. GPT was one of the most straightforward proposals following to attention is all you need. And what they do is that they take the transformer cell and don't do an encoder-decoder architecture. They just do a language model. Yes, something that takes a context and produces new words following that context. A language model, the most common example in everyday life is autocomplete in a cell phone. Yes, they stacked 12 in the original paper. They stacked 12 transformer cells and trained this into a large amount of text, and they find that this language model is very effective. Interestingly, because this result is so a straightforward follow-up from attention is all you need, is that they don't even publish this as a paper. They don't put this into archive, for example. It's almost like I wouldn't say a blog post because it's an actual white paper, so it's a tech report. But this is the start of GPT, that this very straightforward use of the transformer cell now has taken over the world with GPT-3 and ChatGPT and all these other variants. So it's very effective at being trained with a lot of data. So in the original work, what they were more focused at that time was to say, hey, we have this system, this language model trained over a sizable amount of text. Let's see all the things we can do using it with transfer learning for other tasks. Yeah, and that was when we discussed this a little earlier in the lecture, when we talk about transfer learning. You remember all these examples of how we can use it as a part, for example, for doing inference, and then tune it as a Siamese network and things like that. Yeah, But the thing to remember from the architecture perspective is that GPT was not innovative on its own when it came out. The key exciting part is that this architecture scales to massive amount of data. And because it's just trained on text, yeah, there's no shortage of text available to train, and the latest systems are trained on full web crawls. GPT-3, for example, has 175 billion parameters. This amount of parameters escapes well, my imagination for sure, and it's trained on 45 terabytes of text data. And then for larger models, I don't know whether this is as known and popular as BERT or GPT, but I do like it quite a bit. It comes from 2020. It's called T5, and the intention of the authors was to say, well, you know, people will get BERT, they will fine-tune it for a number of tasks that were kind of shipped with BERT. What will happen if we fine-tune it as we train the model? Yeah, so we train the model using an auxiliary task, a mask word prediction in this case, and then we fine-tune it for 16 different tasks. Yeah, but it's not that we fine-tune it for one thing and release the model, and fine-tune it for another thing, we release the model. No, we're going to pack all these different tasks into the same model. It's a research question. Can a model learn all these tasks without forgetting the other ones? Yeah, and of course the question then is how do you access these different tasks that the model has been fine-tuned? For that, they include special tokens, pseudo words that are put at the beginning of the input that allow the model to activate this other functionality. Yeah, and so this is called the text-to-text transfer transformer, T5. And here's an example. You have the system, and you say, you give the input in green, translate English to German, and then you get the output in green. You get the input in green. Is this sentence, you're trying to see whether a sentence is a valid sentence, and you say, well, this is not acceptable. You get an inference whether one sentence entails the other one, and give you a score. That's quite impressive, that the system actually gives you a numeric output. Yeah. And finally, you have a task where you say, well, I want to summarize this piece of text, and given the system will give you. But the beauty of T5 is that it does all these things without any fine-tuning. Yeah, so in a way you can say that you are doing zero-shot learning for all these different tasks. Yeah, and many of these tasks are not necessarily that good. I mean, I don't think you would want to use T5 directly as an English to German translator. I do have used the entailment system for experiment, and it's really good. Okay, so this is for the popular models. Yeah. To conclude, as I mentioned at the beginning, there is this excellent survey that came out last year. If you are interested in transformers, please don't miss it. And one of the things that the survey does is, at the beginning, in figure 2, it goes through the transformer cell, all these different elements we saw at the beginning of the lecture, the multi-head attention, the layer normalization, the residual networks, the point-wise feed-forward network, yeah, the positional embedding, the token embeddings, and says, well, there is so much research now that people have explored variations for absolutely each of these items. And here are the papers that explore these variations. Yeah. So this is really beautiful, because as we approach the problem, we start thinking, okay, they use these positional encodings using variation of wavelets. Yes. What about absolute position? What about relative? What about using other representations? What about learning the encoding, the positional encodings? Well, all those research has been done, and there is some results and some directions, and they are discussed there. In terms of the attention, of course, is one of the key aspects of the transformers, and people have explored a lot of variations. We have some discussion about sparsity, and indeed people have tried sparse attention, they have tried linearized attention, they have tried compressing the attention to obtain smaller tables, also low rank approximation, yes. In terms of addition and normalization, people tried just not using those things and see how it behaves. Yeah. And the same if we don't use residual connections. Yes. In terms of the convolutional the pointwise feed-forward network, people have looked into what happens if we don't use it, what happens if we add more capacity there, what happens if we change the activation functions. Yeah. And then, from the architecture perspective, more interesting to us, people have looked into what if we just break free of this linear combination of this stacking of transformer cells. What happens if we make them into a tree? What happens if we try to make a recurrence of this? Yes. What happens if we use different cross-block connectivities? And so as transformers have become the dominant model and they are so popular, then people have really explored all these different alternatives, and I invite you to look at this, and any of these papers that explore any of these alternatives will be a great topic to present in future seminar presentations. There are also proposals of mixing CNNs with transformers, but for that, and what we are going to wrap up the lecture, most of the work is in special attention patterns. Yeah. So the regular attention pattern is everything against everything. Yes, and that's too costly and produces attention tables that at the end contains a lot of zeros. So the easier way to add an inductive bias to a transformer is with a custom attention pattern. So one of the first things that you can do for a custom attention pattern is to have this concept of a global attention. That is to say, we're going to take in this case, in figure A, figure 4a, you have these two neurons, 2 units at the beginning, and those ones attend to all items in the sequence. Yeah, so you keep this all against all only for 2, and these ones become like a global memory. And this concept is going to be key next lecture when we look at graph neural networks. Yeah. Alternatively, instead you can say, okay, no, I only care about the local context. And then you produce a band attention where each token attends to its neighbors. This, in a way, produce the same output as a CNN. We can take that idea of a band and we can dilate it, and this produces a dilated CNN. More surprising, people have experimented with just random attention. you make tokens attend to other tokens with a certain percentage, and this surprisingly actually works. Yes, this is a way of forcing the sparsity, and I found it somewhat related to dropout too. The beauty of random attention is that, and all these other attention pattern systems is that they have much less parameters to train. And you can also have block local systems. This type of block local are quite useful for visual transformers that we're going to see in the previous to last lecture. Now, this type of attention patterns can be combined, yeah, and the different combinations have different proposed architectures that are used in the literature, like the star transformer that have a global memory and then a band, and other variants. The ones that is very popular, at least in terms of discussion, is the long former. And the long former gives you something that can produce text embeddings over large spans of text, much larger than the 4,000 subwords that BERT takes. And what it does, it has interpairs global memories plus a band attention. And again, any of these papers or attention patterns will be very exciting to present. So now to conclude, I'd like to mention a published work I have using BERT embeddings. So BERT models, the larger ones are multilingual, so they produce embeddings taking input in multiple languages. In this paper I took a web crawl I did of the parliamentary proceedings of Argentina and Costa Rica, and studied the impact of the Spanish dialect on the pre-trained models. And if this is a topic you are interested, or all the data and code and everything is available online. This is using TensorFlow 1.0 and the BERT distribution, so most probably will be a little difficult to run today, but the more interesting part is that all the text is available. And if you're curious about the results, other impacts, other aspects of the input, like task, impact the results much more than dialect, but dialect does have an impact. And well, this is all I have for transformers. Look forward to the next graph lecture. Thank you very much.